Hello.
Yes, sir.
So, yeah, sorry, there was some
So welcome.
interruption.
Yes, yes, sir. Sir, are we ready, sir?
Just a minute.
Okay.
Actually, there was a power cut.
Okay, fine. No problem.
I was like, just, बेटा आवाज नहीं करो. Okay, sir, shall we start?
Yes, sir. Yes, sir. We can start.
Yeah, okay. I hope it is okay. The lecture is fine.
Yes, sir. Yes, sir. It is very interesting. Actually, I think. Actually, sir, we have a quite silent group of participants. I have been observing, sir. So, they are sharing good feedback, sir. In the last 3-4 days, I'm receiving good feedback from them. So today also, hopefully, I think we are going good.
Okay, so yeah, basically, okay, let me share my screen. Can you hear me? No?
Yes, sir. Yes, sir. I can hear you.
Nee, before that, we were able to hear me?
Before that, we were not able to hear.
I think I was speaking.
Okay, I thought you were about to start, not yet started. Okay.
Sorry, sorry, sorry. See, I was speaking, and
Oh, acha. I
okay, I
thought that.
think I have not unmuted.
Okay, okay, okay.
So, what I was saying that in a BEV, in a pure BEV, we have limited energy, right? So that is what is stored in the battery. So, so how we all worry about range, like since we have a battery and it can, it can. Uh, it can lead to very anxious situation when we are in the middle of the road and battery is discharged. So basically, the range is important term. But range is not independent of the driving cycle. So it all depends on where you are driving your vehicle. You can drive on a flat road, on a highway where there is no traffic. But same vehicle when it's going in an urban setup where you have traffic conditions and all that. Okay, I think there's a lot of noise. I will just come back.
Okay, okay, sir.
Yeah. Sorry, all of you. So I think.
Yeah, it's okay. No problem.
So basically, I was telling that this range calculation is important in BEV, but this range calculation is highly dependent on how you drive the vehicle. So it is called driving cycles. So basically, let's say when you let's say I told like when you design a vehicle and you manufacture a vehicle, you go to ARI for testing and certifying and all that. So that is so first of all they will tell you what is the ABC constant for your vehicle, and they will also check the performance which you have claimed, but they can find out whether the performance calculation part you have done is matching theirs or not. And in that, no, let's say you claim, right? So when you go and buy, or even if you see any ads in TV and all that, so we see that they're claiming 350 and all that, right? They keep claiming a lot of things. But there's always a star. Actually, that star is very important, which we generally don't read. So let's say even for a petrol-based vehicle, like they will say that uh, what is it? The average, yeah. The average of a vehicle is 25 kilometer per liter of petrol. But that again there will be one star actually. That star is very important. 25 kilometer per hour only when you are driving at a constant speed of 45 kilometer per hour. Otherwise, not. So we should not we should not read just the lines. We should know the conditions as well. So so for that, no, for that, let's say, but as you can appreciate that the range depends on the how you drive the vehicle. But the driving pattern is not in your hand, right? If you're in a highway, you can drive at high speeds without any brakes, without any turn on and turn off. But when you're in an urban kind of thing, traffic conditions are not under your control. So and even let's say you have how many flyovers, which route you take, and all those things. So to up now, let's say ARI, how it will tell you what is the range, how let's say for a vehicle, how it will calculate the range. So there should be some kind of standards which has to be, standard driving cycle has to be taken. So against each driving cycle, you can tell, okay, for this driving cycle, the range is this. For another driving cycle, range can be different. So that's why these are related. So there are standard driving cycles which are used for benchmarking and even comparing fuel economy and emissions. So all actually all are important. Uh, so in so other countries actually are ahead in terms of this electric vehicle and even the the regulations and other things. So in US there are a lot of driving cycles which are popular, which is called FUDS, that is urban federal urban driving cycle, federal highway driving cycle, and I think I don't remember this name. So then other things are the US 06 and all that. So in Europe there is EC15, EC47. Japan, there is a very useful standard actually. This SAE J227 is highly adopted everywhere. So these are the driving cycles. So this is urban driving cycle, right? FUDS. So it is understandable that you will not be driving at a constant speed for a long time. So let's say when you come out of a signal, you increase the speed, and then next signal you have to again bring the speed to zero, like that, and some stretches of the between two signals can be more, so that you can even drive faster and at higher torque and all that. So it is a typical urban driving cycle. Similarly, I think this is a kind of highway kind of thing. So in highway, you don't do too much of braking. You don't stop the vehicle. Speed may vary, but hello. Similarly, this is the US 06. So I think is a different pattern, like depending on the route. This is European EC15. So you can see that there is a positive dy dt, constant speed, negative dy dt, and these are different. Here it is higher, and this constant speed are also higher. Again, it's this constant speed are different. So this is basically, I think, this type of. So you will, you will. This will give, they might have some kind of data collection and all that, and based on these different dv by dt and different cost speed range regions, they can find out what is the fuel economy and what is this is a nice thing actually. This, so even during a stop and stop, we sometimes go to a higher torque and higher speed ranges. Actually, we have seen even here, right? So that way. So this I was talking about this Japanese thing. So actually they have not. So they have done a combination of all this. So they tell that, okay, you have a acceleration time, you have a de-acceleration time, braking, what they call. Cruising means you're going at a constant speed. Then this is a kind of coasting. You are in a neutral. So this will help us. This is equally important period. Let's say when your engine is stopped. So in this case the motor is stopped. Neither it is motoring, neither it is generating. It is just floating. And so this time can be varied. So all the flexibilities are there. So this 227 and 227A, B, C, etc. There are a lot of variation to that depending on these numbers. So against this, you can tell key for if it is the thing, what is the range? If so, that's how the thing is there. Now, actually, so let's say if you have to model the whole system, I was telling about the modeling thing. So this session is about modeling. So this is a system. All of us know that battery, power converter, and motor, then gear and transmission, wheels, and this driving cycle, driving profile is not your hand, right? So it can be anything. You may also supply some power to the accessories like power steering, air conditioner, heater, and all these things. So this is the total simulation, and so this what need to be done for a full simulation. So we are covering this part, and power converter and drives and all battery modeling we are not doing, but it can be added later. So how we do modeling? So we start with assuming a battery is charged to full SOC. Then so this is the one input parameter. Another parameter is driving profile, because driving profile you have to load. Then estimate distance covered and add, calculate the traffic effort. So this is an iterative kind of thing. So calculate traffic effort, motor input power, battery output power. So basically, so this driving of with this driving profile, we'll know that what is the wheel torque and wheel angular speed. Then we can know motor angular speed, motor torque. So based on this, what kind of voltage and current rating for the same power rating, we'll know that what power is coming from the battery. And so this average power, if we integrate, we'll know what is energy coming out. So when when you're de-accelerating, actually power is fed back. So in motoring, we are giving power from the battery to the wheel. But when there is a negative dt power, so it's basically sometimes power is taken out from the battery. Sometimes power is given to the battery. So we have to start with a definite battery energy, and then we should keep we have a driving profile. This is all I put. Then you keep on repeating that, and until your battery charge comes below a percent threshold. We don't go to zero. So roughly we actually, for a good thing, like people decide, okay, if you are 50% drained, and then we should recharge. So so there is chemistry involved, and different manufacturers suggest different things. We don't go to zero battery, because if you often do that, it may not recover sometimes. So this basically, so for driving profile, we will keep running and you will keep calculating the energy coming out of the battery or going into the battery. And so we will find that, you know, when the state of the charge of the battery is below the threshold, you continue this. Otherwise, you have to stop and you calculate that whatever distance you have moved, that is your range. So this is how it is done. So how to put this all in, you know, kind of again simulation. So we have already discussed part of it. So basically, Simlink is another platform where we can do a lot of things. So actually, we have earlier we have seen the basically M-file approach. But we can also do, you know, Simlink kind of thing. Simlink, actually, a lot of us is quite familiar, and it's another way of doing things. It's not command window type. And sometimes more handy, because if you do big simulations, actually I'm more comfortable to Simlink, because Simlink has a lot of you know, other you know, machines, power converters, battery models, so they all can be coupled, right? So if you do this modeling also in Simlink, it will be very handy. So we know this, I know this equation we all know. So we have to write this equation in always d by dt form, and then we have to write this in Excel form, integration form. Sorry. So so this motor torque, Excel. So it's okay. So this we have come. We have to write in terms of, you know, this Laplace and S transform. So this is easy, like the same thing. So what we have done, basically, this is the thing, you know, how to construct this. So this is the motor torque, what is given to the block, and you have so let's say you have some system. So it has a motoring torque and all opposing torque. So, and then this is the accelerating torque, right? So if you have a, this is the motor torque and this is the opposing torque. The difference of them is available torque, what you have available for accelerating. So this is acceleration torque, and acceleration will give you certain, you know, speed. So this speed is again, you know, used for calculating these opposing torques. And you can also give angle, right? So depending on whether you're moving in the slope or not. So this is also, so mg, otherwise if theta is 0, this mg sine theta, this gradient force will be 0, otherwise it is not. Okay, so basically, so with this, no, you can calculate, you can make some box, so you can make a subsystem where these are the input parameters, and you can even do that performance thing what we have seen, right? And also, so in this block, you see, we can also incorporate this constant torque, constant power, and constant speed regions. So we know that in constant torque region, T is constant. In constant power region, the T varies as inversely proportional to speed. And in the constant speed region, actually, we apply torque that is enough to support the losses. So these all things are incorporated now in this model. So you can appreciate that, you know, we have moved from the M command window to the Simlink kind of. So we all know this, the moving from constant torque to constant power are all dependent on speed. So you apply the full torque when the speed is under V rated. So when the speed reaches rated velocity, you move to torque which is inversely proportional to speed, so that power remains constant. And when you reach your, you know, the maximum speed, you only support losses. So these are all speed dependent. So speed will only decide this block, this block, this block. So basically this is the simulation, you know, like this is the constant torque, constant power region. This is this is the torque curve, and this is the power curve. So power is, you know, in kilowatt. So this in constant torque region, power increases from 0 to full, and then it remains constant. And here you go to constant speed region because you don't require any accelerating torque. So yeah, speed is also here. So maybe I show you in the same link. So this is what I was showing. So basically, so these equations, what we just say equations we have, we can always bring it down to. Uh, so this ETXL is what is coming from motor. So motor torque we have found suitable gear ratio if you submit this TM has become TXL by using this gear ratio and efficiency, and this is a TR which is resistive forces. So that's what it is. And these are ABC constants. So ABC also you can write this in ABC form, right? So this T resistive you can, if you know the ABC, you can always write as a function of speed. And this is what is more generally available for each. So this is a airport route, so you can see, you can hear the sound of the aeroplanes also probably.
Yes, sir.
So
No problem, sir.
yeah, so IT actually every 5 minutes when aeroplane passes. So airport is nearby. So so this actually you can appreciate that this can be easily let's say if you have a simulation where you are running a induction machine or PMSA machine using a power converter, this can be easily clubbed here. So that's what I will show you also. So moving to Simulink is that's why it's a good idea. So let me run this basically. So basically, this is some 2015 Nissan Leaf EV. So Nissan Leaf data is there. The power rating is 80 kilowatt, torque is 254 Newton meter, maximum speed is 150. So and they have, so we know this ABC constant of that vehicle. So let's say if you take a Nissan Leaf or any vehicle, and if you have these parameters with you, you can do all these simulations and find the performance. Actually, they might have claimed some performance, but you can calculate on your own. Well, you can check it. That's what I mean. So let us run this M file and then let us see. Okay. Yeah. So whatever I've shown in the slide, actually this is coming here. So basically, you can see that it has. I think I don't know how to do that. Uh, how you invert colors? I'm slightly poor in this, so I hope you can see this axis. So it is taking roughly 27 seconds to reach the maximum speed of this 40 kilometer per hour. And so let's say if we can change some parameter also and see how, let's say instead of torque of 250, let's say if you have a bigger machine, let's say machine which has a more torque, then what will happen? So this. So at least actually, let's say in all our research institutions, at least we can start modeling and simulating and creating a kind of so that let's say if you go to industry, actually most of us don't make this, because what if our students goes to industry and they should, if they industry know that we know this kind of analysis, it will be beneficial for the student to get the job and all that. So, yeah, so what has happened, I don't know. Yeah, actually, if you increase the torque, I think it was able to accelerate more, and I think other things have already limited myself. So only if this we have increased the this basically your ramping up will be faster. So earlier I don't know how much it was. So now it is almost 2 seconds or two, even less than 2. So earlier it should have been less. Okay, maybe I should have checked it earlier only. So now it is 2 seconds, but so means other things are we already done as performance of speed. So if you increase the initial torque, only you will get the help in acceleration. Other things are already tied up as a function of even your constant power region should reduce. Uh, so that you will get much better performance even in constant power region also. Yeah. So yeah. Oh. So definitely, actually, it was so it was earlier, I think maybe 3.5 or something, which was reduced to 2. So if you increase the torque from 250 to 400, so this has improved, and so this acceleration was much better. So like so somebody has to decide what is the power rating. So if you increase from 250 to, if you are increasing 1.5 times or so, your power rating of the machine will be also increased to that amount. So that's what we have to check. Another interesting thing actually, which is like that. So we are talking about these driving profiles, right? We were discussing here about these driving profiles, right? So why can't we do this kind of checking? Like put this driving profile and let us check. So that is the what I have done later. So there is something called one block called signal builder in Simlink. So that is a very interesting block. Rather actually, otherwise you can also do it without this, but here some kind of automatic programming will be done. So here you can choose these points. So so this is very similar to what I was talking about, this SAE, right? So this this kind of thing. So here I'm missing this, but that is three regions can be easily implemented in this. So this you can vary this point here. So if you let's say so this is the let's say we want 0 to 30 kilometer per hour in 15 seconds. Then you have a constant speed region and then de-acceleration region. Okay. So if you do this, then so this is the speed, and actually we have to find out now. So basically, the slightly different thing is like. So here we are giving a driving profile, and we have to find out if we want this performance. So then, what kind of torque and power rating will be required? Actually, we are not knowing in advance what is the power and torque rating. Here we are giving this directly, and we are giving velocity and dv by dt. We will find the force required to operate these things, and if you have already decided on gears and all, we can find out what is the motor torque rating, motor speed rating required. So this is a reverse calculation, and that is this is actual calculation. Basically, you can say that. So if you want to have this kind of speed thing, so you need to operate. This is a constant torque region. This is constant power region here. Constant speed. So this is torque. This is speed, and this is torque. And here you can see that. And when you so basically you can see that after this speed, actually you are moving to constant power region. This is W max, but this is W rated. So you are constant torque region only up to here. But if you want to go above this, you have to go to constant power region. So basically, motor has to be rated for this condition. And you go to constant speed, and constant speed do not require much torque. While you're coming down, also, since you are already gone above omega rated, if you want to come down, you have to go through constant power region initially, and then constant torque, and come back to zero speed. So very interesting. So you can see from this also, this confirms from here also. This is power. This is torque. This is power. So power is increasing up to this constant, very less power, then because constant speed, then constant power, again coming back to zero. And so this is, and the last one is the energy. So energy is basically integration of power. So that energy also you can plot. So energy required, for going up, but some energy can be recovered in this. So you can see that the energy is required. So energy is already you're depleting the battery, but a lot of regeneration also happened here, and some part you can able to recover. It will take some time, so we'll move ahead. So here, with respect to this, we can we have changed, so it is 10 acceleration, 10 deceleration, and 5 seconds for constant speed. So in this case, so slightly, so here you can see that you have a larger deceleration region compared to the previous one, so you are able to recover more energy compared to the previous one. Otherwise, and it is opposite here. So 5, 10, and 10. So here actually, no. So what happens? Let's say you this deceleration region is not in your hand. Too much. So you need basically how you will do that. It all even depends on. So, uh, this is not in your hand always. But this is important. You can see that the energy, and the variation of energy and the power, so you are having wider this power region compared to this power region. But this is not in your hand always. So this is the simulation what I was talking about. So this is the mechanical system what we have. So this is this with all this embedded, and then this is the signal builder block, and so let us see some simulation. Yeah. This first simulation. So this is a velocity profile. This is so we have decided that this is our omega rated. So this is torque, constant torque region, but this is a torque waveform. You're moving to constant power, then constant speed, then coming back to constant power, constant torque. This is power. This is energy. So we can move these points. So this has changed, and so therefore this has also changed. So means this can be, like we can play with this thing, and so actually that what I have for actually for this session, many things, but acha, again some more things actually I can show you. So how we incorporate this in the so you can see in this yeah, so you can see, so this basically, so driving profile is not in our hand, right? So driving profile, let's say it comes from the road condition and where you are driving, but output of this is torque, and this is our load torque. Basically this torque has to be given by motor, not, so this has to be torque, who will support this torque. So for delivering this kind of torque velocity profile, this kind of torque is required, and who will provide this? It has to be provided by the motor. So actually in our drive simulation, this is a drive simulation of DC machine. So basically closed loop simulation where you do speed control and current control, PI controllers, and here you have a power converter, DC-DC converter, And this is the model of a separately excited DC machine, right? The armature voltage and the field flux, like can be PMDC. So this is so here in this, no, we generally require the load torque profile. So in this, you give in the model of a DC machine, you give armature voltage, load torque have to be given. So this load torque from will come from where? Who? What is the load? So the load is, this thing can be coupled. So this torque, this whole block can be, this T motor can be T motor is basically load to this machine. This machine has to support this load from suitably varying this, armature voltage and armature current. So there it completes, the whole thing. And this is a power converter. I mean, basically, this is the, chopper. And chopper also needs the, so this chopper needs the DC voltage, right? So the DC voltage will come from the battery. So battery, power converter, machine, drives, and this T load will be taking from the driving profile and the vehicle dynamics of the battery, of the system, mechanical system. So basically, this is how the simulation is done. You take any battery, power converter, machine, control of the machine, load profile, velocity profile, system dynamics. All these things will be in the same thing, and it's possible to do the whole simulation in Simulink. So actually, that's all from my side. I think that's what I thought. Something else I can discuss, but I think we should have some question answer session also if someone participants want.
Yes, sir. Yes, sir. Thank you very much, sir. Very much like informative, and I think we got to learn so many things. Participants, kindly, if you have any questions or any doubts, you may please come up. You can unmute yourself and you can ask. Sir, I have a few questions from my side itself. So, can I?
Yeah, please.
Sir, one very interesting thing is where we have to limit the speed, and sometimes we need the acceleration to be in a quicker manner. So, like we need to do certain kind of modification, like in the design, right, sir?
Yeah.
So initially, because otherwise, like if the acceleration is made too high, then it may go up to a very high speed, and ultimately we may end up having a motor of like high rating, and which is not desirable in the ultimately when we come to the steady state, sir. So, sir, my question is is there certain parameters which are limited in the design, like we cannot do this kind of modification even if we want in the parameters? Like suppose we are doing the modeling, fine modeling, in the modeling we can change or modify the values. Sir, is there any parameters like which are limited by the design, actual design, practical design?
Yeah, see, once you have designed, when you have designed the vehicle, so let's say vehicle dynamics parameters are already fixed. So let's say you can change the quality of tire. You can once you design the mechanical system, you can't do much. So you can do, you can change the gears. Gears is possible. Gear change is possible. You can change the motor. All these things are, even the battery voltage, battery current, all these things are possible to change, right? But the
Yes.
vehicle body you can't change. Yeah. So so basically, actually an interesting thing is like, let's say you've designed the vehicle for a flat road, okay, So and the maximum elevation you can go is, let's say, 6 degrees, 8 degrees. Okay. Now, basically, you have a requirement to use that same vehicle. Means you have a requirement to use that vehicle in a hilly region. Okay. Now, what to do? In a hilly region, if the slope is high, it means that you require more torque.
Yes, sir.
But you can't have more torque, right? Your rated torque is fixed by the gears, right?
Mm-hmm.
So
Yes,
what you can do, like you can introduce, you can change the gear ratio. You can change the
correct.
gear ratio from 10 to 15. Then that vehicle is suitable for hilly application. Well, what you are doing is you are converting that power to basically a higher torque and lesser speed. So in a hilly
Yes,
region, it can operate, but you have to sacrifice for the highest speed you can work on. So that alterations are possible,
yes,
and
sir.
that is actually that. So that matlab, that
Mm.
is easily can be done, I think. Mm.
Okay, sir. And those coefficients that was there in the equations also can have some, I think, impact in the design and all, right, sir?
Yeah, but yeah,
Yes.
but how much you can change once
Okay.
once you have, but this have, there's a continuous process. See
Okay.
what happens. Let's say if you're working in a company, let's say you're working in Tata or Mahindra R&D.
Mm-hmm.
So like our students, do work there. So every year na, they want better performance, right? So
Okay.
that is the target. So same
Right.
vehicle is same. Now,
Right.
okay, how can you improve the performance next year?
Mm-hmm.
So that's what they do, right? So they sit on this kind of iterative simulation and try to see, which is, let's say you can do something in the machine. Let's say it's also possible to use a machine with a slightly higher efficiency. So you have used a machine which has a 89% efficiency. Now you can use the same power rating, same torque speed machine, but with efficiency of 91. So that is not an easy process, right? 2% efficiency increase is a horrible job. It's not easy. So probably you can use a new material which has come recently or something like that. So somebody will work on design and increase efficiency. Okay, 10%, 0.1%, 0.5%. So they will do that. Somebody will work on power electronics. Somebody will say that, okay, I am using MOSFET based converters, silicon. Then okay, how to increase the efficiency? Okay, let us go to silicon carbide,
Mm-hmm.
where your magnetics can become smaller. Your efficiency is much better. Your even thermal thing is much better. So that how they don't wait for the best thing in the day one. So they release with the whatever available to them so that they come to the market, and every year they will improve the same thing. So
Mm.
so with each component, how can you improve? So actually, in electric vehicle, the efficiency is the buzzword. So
Mm-hmm.
because energy is limited, so how to increase efficiency? How to increase efficiency? Or either increase the efficiency or decrease the losses. Both ways are same. So
Mm.
so they attack on each thing. So I know people two-wheeler vehicle people, or low power four-wheeler. So they have launched. Then now their target is how to increase the range. It means increase the efficiency. So they will come to us. Okay, what we can do, what we can do. So that's how things. Uh, go
Okay,
for.
sir. Yeah. Thank you very much, sir. Participants, if you have any queries, any questions, please come up.
So what is the temperature in Arunachal Pradesh now?
Sir, temperature is cool. It's very cool. Cold means not very cold, but then it's okay. It's cold means we are actually in the junction of a hill and the plain. So we are just near the border of Assam and Arunachal. So
Okay.
till up to our place, it's plain area. So humidity is little bit high. Otherwise, it's not very cold. That cold. It's not that cold. If we
Okay.
go move further towards the hilly area, it's very
Mhm.
cold. Yeah.
Okay.
I think well then I think sir has clearly explained all the things. So I think people are not left with any doubts. I feel like that. So thank you very much, sir. Thank you for your precious time and provided us with the valuable inputs on the vehicle dynamics and the molding. And sir, we are looking forward to see you in the future as well. Means if any such kind of events are there, sir, kindly allow us to invite you more in the future. Thank you very much, sir, for joining with us despite your busy schedule, sir. Thank you, sir. Thank you very much.
Okay. No problem. Uh, so sorry, I was, I was not interacting too much with you. But actually, yeah, it's a quite a busy schedule. I don't know. This
Yeah,
online thing made us, more busier compared to it.
I understand, sir, and we are also like in the same.
Yeah, I mean, actually,
Yeah.
the in person is more, we are less busy.
Right, sir. Right, sir.
Okay,
Uh,
okay. Thank you. See
yeah,
you.
sir. Yeah. Thank you very much, sir. I will contact you again for the rest of the formalities later on in the email, sir. Thank you, sir.
Sure, 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 sure.
Okay.
Bye-bye.
Okay. Yeah. Bye, bye, sir. Thank you, sir.
Yeah.
So, dear participants, thank you for joining. And we have our second session, sorry, the third session, the last session of today, will be handled by Rajendra Kumar sir again. We will continue with the drive cycle analysis. So, we will meet up again at 3 p.m. So, see you in the second half at 3 p.m. So, thank you very much for joining us.